Okay, so welcome back to the next video. And in this video, we're going to start looking now a bit more details into tractions. Okay, so tractions is nothing funny or nothing freaky. It's really just a fairly simple concept, and it's a concept that opens up the door towards rating what loading we apply to the outside of the body towards the inside. So that's only from, if you recall from that little, let me just write it here maybe, let me see where the boundary, you can write the potato here. Remember that potato that we had, where we said essentially we could apply some point loads, we could apply some distributed loads, and there was maybe some body forces involved. And essentially this is the thing that we've sort of omitted, these tractions that we could apply. We haven't really looked at how does this now connect, these tractions connect towards the stress tensor. That is still something that is not quite so clear. Okay, so this is what I want to make sure that we explore in this video. Okay, so first off, what we can have is just quickly talk again about the traction in terms of, let's start off with sort of a body, and I've got maybe some loading that I'm applying here. So let's call this negative F, and let's say this side. I'm cutting this body now just by myself, and saying I've got another loading here. Okay, that is essentially called positive F. Okay, and I can now say this is a normal to this face, and then this is going to be the negative of the normal on that face. Okay, and this normal vectors and these forces that we have as vectors, we express. Let me just put the thing there. We express in this coordinate system. So what is important about tractions to understand and stress tensors is it's all about coordinate systems. Okay, so we're expressing these components of this and this vector in terms of this coordinate system. So this vector here has components nx and ny, for instance. So this is the components that I might have for that. And in this one, we just have minus nx and minus ny. Okay, and obviously this one would have its fx and if it's fy. Okay, and the same for that. So that is what we have. And obviously these forces don't have to be parallel, so they can be sort of generic to these faces. So they are welcome to be at some angle to this, and the same for this, as long as it's such a way. So the question is would this even be in static equilibrium? As long as it's in such a way that things are in equilibrium. Okay, but I just want to make sure that you understand that although I'm looking at this simplified problem, this could be some general loading as long as this body is now in static equilibrium that we're looking at. Okay, that's the only thing. And so this force vector, if I were to just divide it by this area, so if I just say take that force vector, divide it by an area, and then we say that is what we call attraction. Okay, that is essentially what we call attraction. And if I take this area and I take this force action on that area, and I say take this negative F divided by A, then I get attraction out. So all that attraction is essentially, it's something with units Newton per meter squared or Pascal. Okay, Newton per meter squared. That's the only difference between attraction and a applied load. Oh, I'm off the board there. This is again just Newton per meter squared or Pascal. Okay, so that is important. Let me just put that there as an or. So that is just to make sure that we understand that. So two things that I want to just note here is, the first thing is that the direction of a force applied to a body, okay, is equal to the direction of the traction. That is important to understand. Okay, so any load that I have on a face, that traction will have the same direction as that load. The only thing that is important to maybe just mention here is that the difference is that the magnitude of the traction will be different, because I'm taking this vector and dividing by scalar. So the magnitude of the traction will be different to the force. Okay, so these two things are just, this is essentially how traction relates us to a load that I apply to a body. Okay, so let's take maybe one thing here and let's zoom into this part. So you've got the context of the bigger problem, and I've related now sort of loadings at a macroscopic scale that I'm applying to a body. What I'm going to do now is just quickly remind you again of what the stress components are, so that we just have clarity with that, because again, it's related to a different coordinate system, so expressing stuff in a different coordinate system, or at least the tractions in a different coordinate system. That's what it's going to be related to. And then I'm going to zoom in that we start getting towards a point. Okay, so those are the sort of 3 steps that we're going to follow. So let's first get to the place where we're going to get to first looking at really just the details now in terms of how does the stress component look again compared to the tractions. Okay, so let's wipe this off. I'm going to make a zoomed version of this kind of problem, so we can look at that zoomified version. So I'll just do this zoomed version, and then I'm going to essentially stop the video, and then I'll make another video so that I don't get too long. Okay, so that is essentially, so let's look at this. So we've got this body, we've got now this nice coordinate system there. Okay, we've got this normal, so I'm going to just put the normal here at the top, doesn't matter, so it's just a little bit out of the way. I've got a normal, and I could say I also have perpendicular to this normal, I've got let's call it a S vector. Okay, so that is sort of on that surface, or in that shear direction that I have that. And again, I'm reminding you that these vectors are expressed in this global coordinate system. So they have nx and a ny. They have, this has got a sx component and a sy component. Okay. And what I can do then is to say, well, on this body there's some traction. Okay, so I'm going to say, let's say the traction is this. This is now my traction vector. And this traction, as we've spoken before, always have the superscript just to indicate which is the normal that we're talking about, which is the traction on which face. And so this is the face that we're talking about. This is the normal that's associated with that face. This face would have its own normal, so this face would have a different normal. This one we could maybe call the vector nx, write it like that. This one could, sorry, ny, what is this, x, ny, I'm just writing that. This could be the vector nx in this direction here, or I could maybe call it negative nx and negative ny, because they're in the opposite direction of that. This could just be, on that face would be sort of ny vector, okay? And then I could have, out of the plane, I could have on this side, depending if which direction my z is positive, I could have the nz and negative nz. So those are the normals that I could have acting on there. And all I'm going to do is, this thing that we now understand what it is, okay? This traction is just a force divided by area. Same direction as to any force that I have. So one thing I can tell you by just looking at this, that the force acting on this face is in this direction. And the magnitude of that force, first I have to go and compute the area and multiply the traction by the area. Boom! And then I recover that force that I applied to that face. That's it, okay? Nothing more than that. What now is important to understand is if I take this traction vector, okay, and I express it not in components. So this is the way the traction vectors always, the components are, in terms of tx and ty. But if I say, let's express this traction vector, okay? Let's rather say, I'm now going to express this, not in this coordinate system, let's do it properly. This coordinate system, I'm going to express the components of this traction vector in these coordinate systems. And that's it. That is what we will call stress components. So essentially, if I take this traction, n, which is now this vector, and I dot it with n, and I just say, let's dot it with n. So what I'm doing is I'm taking this vector and I'm projecting it on there, and then I'm seeing how long along this n I have to walk to get this length of this vector. Okay, so I'm just dotting it with that, and then we'll call that essentially sigma. Let's call it nn. Okay, which is now the sigma component related to this n direction. Okay, and then I can say this traction vector, I'll do it this side, this traction vector, I can dot with s. Okay, if I dot it with s, I can say, let's call it sigma or tau, it doesn't matter, and then the normal is for the direction of the traction. Okay, and the force or the stress component is going to be in the direction of s. Okay, and I say I call it ns. So here I will call it sigma nn, because n relates to the normal of the face and n relates to the direction of the shear of the stress component. And so what I've done is now I've expressed the same vector sigma n in a different coordinate system. So this lives in the coordinate system now ns. Okay, that is essentially all I've done now, is to say take something that I'm familiar with and relate it back. It's familiar with in the normal global coordinate system. Now we're going to relate these things in a different coordinate system. And again, I'm going to remind you why this is beneficial. The benefit is if I have something like this, where I'm pulling in tension, like I've explained in that previous video from last week, but let me just quickly recap that. If I were to apply a load F here, and that F will be negative F on this side, if I have my coordinate system like this. Okay. The problem is I would like to express this in terms of stress components as something that is in tensile, tensile stress. I can't do it by having this coordinate system, but what I can do is to say, let's create a coordinate system for this face, and this is this coordinate system here, and let's create a coordinate system for this face. And I'm going to call this negative, negative, okay, because that's n and s already defined, opposite direction, negative s, opposite direction to n, negative n. And now, if I were to express this force divided by the area to get its traction, dotted here, I will get it as a negative force dotted with a negative n, and I will get a positive component for the stress, normal stress out. And that is what I'm gaining here. If I have now problems that are in tensile, where I'm going for these stress components, I can now express it as a positive quantity for stress when it looks like this, the loading. Or with compression, I can get it as a negative quantity. Okay, and that is the important thing to understand. And you could see why it would be negative. If this vector was in this direction, then and the force was in that direction, that will be in the opposite direction to each other, and so it will be a negative dot product that I'll get out there. Okay, and so this is really what we're buying with going for the tractions. Is we are now allowing ourselves to get to a quantity where we can talk about positive for tensile and negative for compression. Okay, and this is why these local coordinate systems are so important. In the next video, I'm going to take it one step further. Thank you.